All right, welcome back. We're going to prove a couple theorems here and then talk about some other specific kinds of subspaces of Rn or Rc or however many entries you have. The first one is about the null space. Let's remember real quick the definition of the null space of A. It is the set of all vectors in Rc that have C entries, so that when you use those entries as weights in a linear combination of the list of column vectors, you get the zero vector as a result. So let's prove that this is always a subspace. We need to prove that all three of the conditions are always true, no matter what A is. So the first thing is we need to show that the zero vector is in it. Well, sure, because if you do 0 A1 plus 0 AC, that's definitely the zero vector. Okay, we got that. Let's show that's closed under vector addition. So we're going to assume that we have any two vectors in the null space of A. That means when you use the entries of these vectors as weights of the columns of A, you get the zero vector as a result. Same with Q. Now we want to show that P plus Q is still in the null space of A based on this assumption. Of course, the definition of P plus Q is where we add all the components, like so. Well, let's see. If we do P1 plus Q1 times A1 and the rest of the way through the rest of the components, do we get 0? I claim that yes, we do, because what you can do is use the distributive rule to distribute the A vectors into each of these. And that's going to give you the following. And if you just rearrange the terms, what you get is 0 plus 0, which equals 0. Cool. Okay, so that means P plus Q is in the null space of A. Let's do the same thing with scalar multiplication. So we're assuming that we have any scalar and any vector in the null space. So we're assuming that this is true. Same thing as before. And we want to show that that scalar multiple of P must also be in the null space. And it is, because when you do this linear combination, you can factor out the K. And we assume that this whole thing is the zero vector, because P is in the null space. So K times a zero vector is always equal to 0. So there we go. That means K times P is a vector in the null space as well. And we've got that. So yeah, the null space of any matrix is automatically a subspace of Rc. Quick little extra credit exercise. It turns out example 4, this set P is the null space of something can you tell me what is that matrix that is a null space of? And when I say extra credit, I mean not actual extra credit. Give yourself mental extra credit, satisfaction of figuring something out. Let's look at Theorem 12. Spans are subspaces. So if you have any list of vectors in Rn, then the span of those vectors is a subspace of Rn. Let's prove it. The first thing is the 0 vector in the span? Yeah, we've talked about that before. You can always multiply all of the vectors by 0, and the result you get is 0. So there it is. Is it closed under vector addition? So we want to show that for any two vectors, P and Q, that are in the span, that their sum is in the span. But we could just write out what does it mean to be in the span. It means you can write P as a linear combination of the list of vectors A. Same thing with Q. So that's what it looks like for two vectors to be in the span. Now, what P plus Q is the sum of P and Q, obviously, but we can write it like so. There's P, here's Q, and we're adding them together. Now, we could rearrange the terms, like get all the A1 terms together, and also factor out the x1 plus z1. And do the same thing with all the rest of the terms, up through xc plus zc, factoring out the ac from that. And lo and behold, we have a linear combination of the A vectors. So we're good there. Let's prove part 3. We can take any vector P that is in the span and any real number K. And we want to show K times P is in the span of A1 through AC. And of course, Kp can be written K times this linear combination. And when you just factor the K in, yeah, it's just another linear combination of the A vectors. It's just that all the coefficients are now K times bigger, but it's still a linear combination of the A vectors. And so we've proven that all 3 of the conditions are met. Cool beans. Let's look at the column space. So whenever we use the word space in linear algebra, we're talking about a vector space or a subspace. So that's why we called it the null space. You might have been wondering back in 1.4 why it was called the null space. What do we mean by that? Well, yeah, because it's a subspace. So the column space, likewise, is also a subspace. We write it as col of A, and it is the span of the columns of A. So it's the same kind of thing we've been looking at in 1.3 and 1.4, the span of the columns of A, but we're just writing it in terms of the matrix A as opposed to the list of vectors, but it's the same thing. Now, the row space of A, written row of A, is the span of the rows of A written as vectors. So both the column space and the row space of A you can think of as the span of a matrix, But that's why we don't say the span of a matrix, because it's not clear which one of these two things you're talking about. So that's why we're coming up with new terminology for column space, because there's also the row space, which is another kind of the span of a matrix. So let's look at an example. Here is this matrix with columns 1, 4, 2, 5, and 3, 6. Let's find a few vectors in the column space first. Okay, one vector that's in the column space is the 0 vector, because that is 0 times each of the columns. Can you guys hear my cats running around in the background? They're feeling a little feisty this morning, I guess. So yeah, that is a linear combination of the column vectors. We could also do any other linear combination that you want. So here's another one. The vector where the first component is pi minus 3 and the second one is 4 pi minus 6. Or if you just take one of the columns themselves, like 2, 5, that's in the column space because it's 0 times the first column plus 1 times the second one plus 0 times the third one. Okay, so yeah, that should look familiar. The row space is a little different. Now, different textbook authors will use different kinds of annotation for this. Some will say that the row vectors are like 1, 2, 3, like this, but I find that confusing. I like to think of the rows as a list of vectors, and I always write vectors using the same notation, like so. So the span of those rows is what we're talking about. So that includes the 0 vector in R3 this time, because we're taking a linear combination of R3 vectors, or any other linear combination that you want, like so. So these vectors are in the row space. So it's easy to find vectors in the column space or the row space. If you want to find a vector in the null space of A, that takes a little work because we need to solve the equation. So any vector x that satisfies this is a vector in the null space. And we know how this is equivalent to the system of equations with the following augmented matrix. We can row reduce this by doing -4 times the first row plus the second row to replace the second row. So -4 times 4, -4 times 1 plus 4 is 0. -4 times 2 plus 5 is -3. -4 times 3 plus 6 is -6. And -4 times 0 plus 0 is 0. Then we can multiply the second row by -1/3. Then we can clear away the 2 above that second pivot position by doing -2 times the second row plus the first row to replace the first row. All right, so this is now in reduced echelon form, and we can write out this equation, and following the method we've been using, solve for the basic variables in terms of the free variable, which is the one that doesn't have a pivot position, which is x3. So x1 is equal to x3, x2 is equal to -2x3, and x3 is just x3. So we can see the null space is the span of this vector 1, -2, 1, because any x3 multiple of that gives you another solution of this homogeneous equation. So if we want to find a few vectors in the null space, you can take any multiple of that you want. If x3 is 0, you get that. If x3 is 1, you get 1, negative 2, 0. If x3 is pi, you get pi, negative 2 pi, pi. Like so. Sounds good. Let's take a break and we will go on and maybe finish the section in the next video.